I'm pretty interested in operating systems and computers and software and all that. So this is just me talking about all of that stuff. Now, first thing is that this is user space on top. So essentially your visual and your graphical user interface, which is what we see of the computer. So how you've got like your taskbar and you've got all your little program icons. That's your GUI or your user space. And your user space, hopefully you understand the idea that the terminal or the shell, which is a command line interface, is the same thing as the GUI in functionality. By that I mean you can click an icon for a program, or if this is like a 2000s or older era, like a video game console, you can flip through menus. Like, does anyone know the PlayStation menus? How you can go like up, down, left, right. With those, they actually made a pretty advanced menu with like the PSP and the PlayStation 3. It's more of a like a locked in GUI that's good for controllers, right? With up, down, left, right, and like yes and no buttons. But essentially the shell, you're doing the same thing. It's again, and these are all programs. One thing to understand about this is that your GUI is a program, your shell is a program. It just gets ran, you're accessing this program, and it's made up of multiple programs as well. There's a lot of stuff going on behind the scenes, right? And then on top of the shell, or the GUI, we run regular programs. So usually it's your web browser or your video games or your like editing softwares or whatever, right? So this is mostly what people see of the computer. The one important thing to understand about the user space is that you need to have file editing capabilities. So really it's just if you can edit a file, you can create a file, delete a file, move around in folders, create folders and do that with delete and edit whatever folders, but also move around with folders. And then you can do that with files, and you can read files and edit files. Like that pretty much is it, right? Because technically everything's a file. If you want to think about it that way, it's just different files. Executable files are just executable files, right? So editing those, because again, ultimately everything's just in a text format, right? That's why being able to control files, edit them, delete them, as I said, create them, is like the most important thing. And then, of course, you need stuff like networking, process managing, and we'll kind of go over some other stuff. So, okay, so below the user space is what system calls, basically. Now, the reason system calls are important is because here's the thing. If you want to run stuff like the shell or even programs, on top of everything, you are going to be accessing system calls. And the reason why is that if you want to create a file, that's a system call. If you want to read a file, that's a system call. If you want to write to a file, that's a system call. If you want to delete one, is that a system call? I don't know. Maybe that's just, I mean, I guess technically you're calling things, changing the disk and memory and all that. So yes, you're probably using system calls. So if you had, just say you had like a random computer, it had no operating system on it, and we then programmed a shell and a GUI, and we have some web browsers, and we have some software and your editing software, whatever that we want to run on it, and we managed to bootload into this, it would not work because we don't have the system calls. Your programming language either translates things back into system calls or allows you to access system calls. And your operating system has operating specific system calls. So depending on if you're using a Linux, a BSD, a Mac, or a Windows, or even if this is on a phone, right? Like the Android phone uses a Linux kernel, so you should have all of the nice system calls for that. The iOS phone uses the same thing. They're going to be essentially different system calls, which is why that programming on Windows software, making Windows software is a little bit different than making Mac software or Linux software, because the system calls are different. Now, programming languages are very helpful and they standardize some of this. For example, if I use the C programming language and I have a compatible compiler on a Linux operating system, it will run just fine, and I can create files and delete files and open files and create, edit them, and do all kinds of things with files, because the C standard library allows me to access the Linux system calls that needs to happen, and it also allows me to access, I believe, the Windows system calls. So it will work either way. Now, things are a bit different if you need to work with graphics, and then you need to work with audio and work with like 3D and certain other things. Then things get a little bit more complicated, but at least if you want to work with text, everything is essentially standardized, which is nice. The same, you would have an open read write fork exec socket, etc. equivalent on Windows and Mac and such, because you need system calls for networking, you need system calls for memory manipulation, you need system calls for process manipulation and scheduling and all this kind of stuff, which is like program dependent stuff, and you need all these system calls just to get this stuff working. To an extent they would be different, but they're essentially, it's the same kind of thing, right? It all works the same. Now, getting deeper, as I said, if you just threw a GUI or a shell on top of a piece of hardware, it wouldn't work because you need the system calls. Now, what are system calls? They are functions, right? They are essentially the kernel's functions. So the kernel is essentially made up of what we would call state, if I understand it correctly, which is essentially just, again, what is everything in a program? It is just functions and data and functions, right? So variables and your functions and your things which do things, right? The state is like all of the different master variables, the master state of the operating system, right? So it's like understanding how much resources it has, what is the percentage and like usage of the resources, and like how much disk does it have, how much memory, how much speed can it handle, all these like master variables, right? I would imagine. And the kernel, one thing to understand, the kernel is a bridge between your hardware. So hardware is a physical thing on the bottom, that's your RAM, CPU, disk, graphics card, networking capabilities, Bluetooth, whatever physical hardware you have. The kernel is just a bridge between the hardware and the programs you're running on the computer, right? It's all this stuff building up to allow you to run programs, because that's what a computer's use is, right? It's to compute things, but really it's to run programs, so to speak. And of course, if we go down kind of to the bottom, so these are 5 responsibilities in an operating system. Okay, this is pretty important thing. So what essentially is the kernel doing? Number 1 is process managing, which means creating and destroying processes. Processes are kind of like programs, so to speak, and then scheduling CPU time, context switching. So it's kind of handling like who gets a CPU and like when does it get it, and like when is things running, because again, everything is linear. Like, believe it or not, everything is linear. Your CPU is handling things one thing at a time, basically. If you've got multiple cores and multiple threads, then it can handle things in parallel, but it's still, technically it's like linear, I guess, if you want to think about it that way. Then we have memory management. So things need to be stored into memory to then be accessed by the CPU, and then it's stored in like CPU memory and cache and all that kind of stuff. Memory management is very important. So memory is almost like the intermediate between your disk, your hard drive disk, and your CPU. It would take forever to access things in the hard drive. In fact, it takes forever to access things in memory. Really, it's the CPU cache that everything's kind of, like from the CPU that everything's happening. But memory management is absolutely important, which pretty much means allocating memory, freeing memory, virtual memory. It's, again, memory is just this collection of buckets or spaces or something, and you have to organize it and make sure every program gets memory, and that program memory isn't interfering with other programs memory, because otherwise things crash. So there's whole lot of stuff that's important. Next thing, of course, file system, which is your files, and really this gets into the disk. The disk is just, again, storage methods. Devices are just things which can store zeros and ones, right? A positive or a negative pulse, etc., of like different voltage readings, whatever. You're turning that through programming, through the driver. So a lot of this stuff is drivers, memory drivers, CPU drivers, disk drivers, right? So it has to handle directories, permissions, basically like file permissions, who gets to access this or that. Do you have the right level of stuff, caching, which is like things that are used a lot, and buffering, such organization on disks. So you're turning just a piece of hardware into something that can be accessed. Device drivers, this is stuff like your input output, so your keyboard, mouse, networking, etc., etc. Translates hardware signals to data. So instead of just like electronics engineering type stuff, we're getting potentially binary signals or even analog signals. You're turning it now into data. And then networking, of course. So you're able to access different computers now. Okay, so here are some examples of system calls. So these are bash commands. We've all seen what copy is. We all know what ls, which is basically check everything, /program, that's you're running things, pinging things, etc., etc., right? You can run these yourself. This is what they're actually doing. These are the system calls behind things. Like you use bash and you think, oh wow, this is really low level, but no, it's actually not as low level as you think. They say it's about, here we go, 1,000 lines for a bootloader, 5,000 for memory management, 5,000 for process scheduler, 3,000 for file system, 2,000 for disk driver, 2,000 for system call interface, and then 1,000 for a basic shell. Give or take, you could reduce a lot of that, but here are some kernel system calls. For example, we have memory, nmap, brk, mprotect, munmap. So if you want to look up these, for example, so again, the kernel, it's all these functions and state. So the one thing I think about drivers is that drivers standardize the hardware to make it so that we can have this. You wouldn't be able to call up memory if you didn't have a driver on your memory, because all memory is a little bit different. There's different speeds, it's different capabilities, it has different like little things, I don't know, caches or whatever. Like it's got different things hardware wise. Basically every piece stick of memory is a little bit different, and each memory probably has different quirks, electromagnetically. So you need something to standardize it, and then we need these functions, which again, it's a higher level thing, to access the memory or to access the device, the CPU or the hard disk or whatever, to essentially turn the thing into a controllable thing that works with the computer, so to speak. And here's another idea of here we go, the C standard library. Printf is actually calling write, fopen is calling open, malloc is calling brk and nmap, and then the system is calling fork, exec, or wait. So you could see that, again, as I said, even if you can get a C compiler onto a computer, it doesn't matter if you don't have the system calls. Otherwise, you're just going to be doing like basic mathematics or whatever, using your CPU as like a calculator, until you can get these more advanced things on there, right? Like you can't access your hard disk if you don't have a hard disk driver, and then the correct kernel states and system calls to be able to manipulate that, if you get what I mean. And then we have kernel down here, so it's got these little system calls to access the hardware, and then of course we have calls drivers, very important. So drivers is like the intermediary between hardware and kernels, system call state, and then syscalls is the intermediary between basically your I guess your hardware and your or your drivers and your standard programming language, or your shell, depending on how you want to see it. Right, so this is an interesting boot sequence. So we turn on our power, the CPU jumps to a fixed address in ROM. This is where we get to the BIOS, which is that's so you turn the power on, and then you see the BIOS screen, which initializes the hardware. So I guess this is starting to access drivers. All right, first bit of the kernel. Reads the first sector of the boot disk, so 512 bytes, and then loads into memory at 0x7C00 and jumps to it. Then finally we get to a bootloader. I'm sure you noticed that's the next thing you see. You'll see a grub if you're using Linux, or you will see disappointment if you're using another operating system. Yeah, basically, so this is where we finally get to understands file systems, finds the kernel file, loads the kernel into memory, sets up basic CPU state, jumps to the kernel entry, and then we ended the kernel, which you'll notice this. It's just before you init system, actually. Yeah, okay. So the kernel loads, which gives you access to pretty much nearly everything, and then your init system will run, which is like your system D, I believe, and then your shell runs, or your login screen, I guess, if you're using a GUI. And here's an example of state or the master variables. We have a process table. Every running program, its PID memory map registers over files. So this is how you have your task manager and all that stuff, or system monitor. Is you'd use all the data from this, and then we have a memory map. So basically, what I look at like what's in memory or what's not in memory or whatever. File descriptor table, every open file, where it is in disk and current position, mount table, which file systems are mounted and where, and then interrupt table, which drivers handle which hardware events. Interrupts like it just interrupts like the code, and then it kind of goes to that. It's like a go-to, I guess. I don't know, more aggressive. Yeah, and here we are again. Basically, it starts. So user space on top of the kernel, which on top of the drivers. Technically, the kernel kind of encompasses the drivers, and then it's on top of the hardware. It depends on how you want to see it, basically. But I hope that kind of explains it. I'm still trying to learn this. I don't know it enough to be able to program the whole thing. I can kind of start to program some user space, but that's about as far as I can go right now. But really, the idea of the kernel being a bunch of like functions to control the hardware and other things, or to allow for like programs to run and all that, and then having all of the state variables and such is an important idea. And then the drivers being just ways to standardize your hardware to get it to work and run, and that'll depend on your operating system standards and such. Makes it a lot easier to understand. User space is pretty simple, as I said. It's just like working with files, right? Working with networking, just getting programs and such to run. Every program is a file, right? And it's all just data that can be edited and such. So anyway, I hope you learned something.